Dear student, now we will see that how we can determine the Young's modulus of a material of a wire. For that, we need a particular type of arrangement as shown in the figure. A typical arrangement to determine Young's modulus of a material of a wire under a tension is shown in figure. It consists of two long straight wires of same length and same radius suspended side by side from a fixed rigid support. Here the upper horizontal line is a fixed rigid support and A and B are the two wires with same length and same radius of cross section. The wire A, which is called reference wire, carries a millimeter main scale M and a pen to place a weight. The wire B, which is also called experimental wire, of uniform area of cross section, also carries a pen in which known weight can be placed. A vernier scale V is attached to a pointer at the bottom of an experimental wire B. So careful, here the vernier scale which is kept at the bottom of experimental wire, which is shown with the arrow. You can see this black arrow shows the position of vernier scale on the experimental wire, but it is shown with this main scale. Actually they are not together. Vernier scale is on experimental wire while the main scale is near the reference wire. The wire B of uniform cross section area also carries a pen in which a weight can be placed. A vernier scale V is attached to a pointer at the bottom of the experimental wire B and the main scale M is fixed to the reference wire A. The weight placed in the pen exert a downward force and stretch the experimental wire under a tensile stress. The elongation of the wire, that is increase in length, is measured by vernier arrangement. The reference wire is used to compensate for any change in the length that may occur due to change in a room temperature, and since any change in the length of the reference wire due to temperature change will be accompanied by equal change in the experimental wire. Both the reference and experimental wires are given an initial small load to keep the wire straight and the vernier reading is noted. Now the experimental wire is gradually loaded with more weight to bring it under a tensile stress and the vernier reading is noted again. Now we can say here the vernier scale which is attached to an experimental wire, the wire has a cross section area A and this wire has a small radius, that is a cross section has a small radius small r. So this area can be determined using A is equals to pi r square. Moreover, when we suspend more and more mass in the pan of the experimental wire, it will experience the gravitational force in a downward direction that can be written as F equals to mg. Now we can say that let small r and capital L be the initial radius and length of the experimental wire respectively. Then the area of cross section of wire would be pi r square as shown in the figure, and let m be the mass that produced an elongation of delta L in the wire. Thus the applied force is equals to mg, where small g is acceleration due to gravity. Now we have already equation of Young modulus, that is y is equals to sigma over epsilon. and here in place of sigma we can replace it with the equation of sigma, that is force over area, and obviously epsilon is the change in a length to the original length. So now when we simplify this equation, the equation will be like F into L upon A into delta L. Now if we replace the value, that is F is equals to mg and A equals to pi r square in the equation, we have the new formation of the equation. By using this formula, we can find out the Young's modulus of the material of the experimental wire, and we can modulus. It is also called modulus of rigidity, and it is symbolically written as capital G. To understand the phenomena, we will try to see that how it can be defined. So the capital G is the ratio of shearing stress to the corresponding shearing strain, and it is called shearing modulus of the material, and it is represented by G. As per as the condition, we can define it, that is shearing stress sigma s and shearing strain can be written as epsilon s. Now sigma s can be written as F over A, while shearing strain that can be written as delta x upon L. So here we will write it as 1 upon delta x upon L. Now when L goes to the numerator, the term will become FL upon A into delta x. But we also know that delta x upon L is also called as a theta. So if we consider that equation, then we can write that G is equals to sigma s over theta, and therefore if we make sigma s as a subject, we can get sigma s is equals to G into theta. The unit of sigma s, that is a shearing modulus, is G, and it is actually having the unit of Newton per meter square or Pascal. Similarly, the G is generally Y by 3, which is indicating that for most of the common materials, the value of shearing modulus is about Y by 3. So it is less than Young's modulus. Y is equals to 3G in general, and we can determine it in a way. So the shearing stress can be represented as G into theta, and G is here the shearing modulus, and it can be determined from the table. It is found that for tungsten material it is about 150 gigapascal, and for lead it is about 5.6 gigapascal only. So this is the comparison of shearing modulus. Dear student, now we will determine the new term, that is bulk modulus. Now how to define this term? Now that we have seen that when a body is submerged in a fluid, it undergoes a hydraulic stress which is equal to the magnitude of hydraulic pressure. This leads to the decrease in the volume of the body and thus producing a strain which is called volume strain. Now the ratio of hydraulic stress to the corresponding hydraulic strain is called bulk modulus, and it is denoted by capital B. Now it can be written as, that is minus P over delta V upon V. The negative sign indicates that the fact that with an increase in pressure, a decrease in volume occurs. That is, if P is positive, delta V is negative. Thus, a system in equilibrium, the value of bulk modulus is always positive. Now, the SI unit of bulk modulus is same as the pressure, that is Newton per meter square. So, here we can say that SI unit is meter per second square, that is meter per second square. Sorry, here it is not this unit, this is the unit of acceleration. The SI unit is Newton per meter square or Pascal, because it is the same term, that is Pascal. The bulk modulus or the bulk moduli of particular common materials are given in the table 9.3 of the textbook. The reciprocal of the bulk modulus is called compressibility. So the reciprocal is called compressibility, and it can be written as minus 1 upon delta P into, in place of bulk modulus, the term will be, that is delta V over V. So this would be V over delta V. So this is the condition for the bulk modulus. Oh, so here in this case this delta V will come in a numerator and the remaining original volume will remain in the denominator. So this is the compressibility. It can be seen that from the given table 9.3, the bulk modulus for solids are much larger than the liquids. Here it is given for different solids. The maximum bulk modulus is given for nickel, that is 260 gigapascal, while for liquids the maximum is given for the mercury, that is 25 gigapascal, and for gas or air it is very small, that is 1 into 10 raised to minus 4 gigapascal. Solids are least compressible, whereas gas are most compressible. Gas are about 1,000,000 times more compressible than solids. Gas have large compressibilities which vary with pressure and temperature. The incompressibility of the solid is primarily due to the tight coupling between the neighboring atoms. The molecules in liquids are also bound with their neighbors, but not as strong as in solids. Molecules in gases are very poorly coupled to their neighbors. And here in the table number 9.4 of the textbook, page number 239, it shows various types of stress, strain and elastic moduli and the applicable state of matter at the glance. So we have to just observe it and we find the comparison between stress, strain and various type of elastic moduli in it for different type of materials.